Milano to open this fantastic location for us. Today we're going to have lectures. The first will be about the physics of atmosphere. The lecturer is a professor of the University of Milano Bicocca. Her name is Claudia Pasquero. Is the vice president of the International Union of Geodesy and Geophysics, and is also professor of oceanography here in Milan. So please, Professor Claudia Pasquero, the stage is yours.
Thank you very much. Thank you for the organization of this wonderful event. And I also wish to thank IBM because this is a really nice location. What I'm going to tell you today is some of the physics behind the extreme event. We often hear talking about extremes and meteorological and climatological extremes, and we know that the climate is changing. So we would like to establish a few links between them and also between things that sometimes they seem to be contradictory. Well, we first talked about climate change using a slightly different wordings. We started talking about global warming. And that's because the very first thing that the injection of the greenhouse gases does in the atmosphere is to increase temperature. And so the very first signal that can be expected is an increase in temperature. And what you see here is a map of the temperature trend at the near surface, in the air, at the near surface, over the last 40 years or so. And you can see that most of the globe are kind of reddish, indicating a positive trend over the last 40 years. You also see that wherever there are crosses, it means that the trends are not statistically significant. Large portions of the oceans do not have any statistical significant trend, and it's due to a combination of the fact that the oceans have a longer memory, so they take a longer time to change their temperature. But also, it's also a signature of the fact that we do not sample things uniformly. And so clearly, over the oceans, we have far less measurements than over land. So it's more difficult to have a statistical significance. We also see another feature in this map. We see the fact that the globe is not uniformly warming. It's not only a matter of statistics, as I said, but it's also a matter of having, for instance, a very large polar amplification. The high latitudes in the northern hemisphere are warming at a much faster rate than the global mean. There is another inhomogeneity, which is related to land and continents, and that's what I was mentioning before. We will get back to this. But the fact the observations show us that the continents have a larger trend than the oceans. There are other signatures of this differential warming. For instance, high altitude, high elevation areas warm at a different pace with respect to the low elevation areas. So there are many inhomogeneities. And we will see that these regional and local changes have an effect on the extremes. I want to start from one of the most difficult signals that there is to evaluate, which is in heavy precipitations. We first start from the observations and then discuss it. But why do I say that it's one of the most difficult signals? Because precipitations is an intermittent signal. So either you have precipitation or you don't have precipitation. So there is intermittency, there is a huge variability. I have nothing, I have everything. So it's based on a threshold. It's a highly nonlinear signal. It involves nonlinear processes, and therefore more difficult. You can imagine that here, where we are right now in Milan, the precipitation, the annual mean precipitation, I'm not talking about the extremes, but just the annual mean precipitation, the cumulative precipitation that there is in a year can vary by a factor of 3 between one year and the subsequent year. So there is a huge variability, an increase 300% next year with respect to this year is kind of normal. And so clearly having those large changes year to year means that it becomes very, very difficult to find a statistical significant change. Nevertheless, we can say something. It's not that we cannot say anything. If you look at any individual time series of precipitation, you would not find most of the times, in the majority of the times, like 90% of the time, so you will not see any significant change over the last few decades. But if in the null hypothesis that the heavy precipitations are not changing, you would expect that more or less, if you take all the data sets in the globe, you would expect that 50% of the stations show an increase and 50% of the stations show a decrease. Not even significant, doesn't matter, but you would find positive and negatives more or less with the same ratio. And instead, we find that despite the fact that an individual station doesn't have a significant trend, there are many more stations with a positive trend than stations with a negative trends in terms of daily extreme precipitation. This means actually the ratio is about 2 to 1, so there is a double. The number of stations with a positive trend is about twice as the number of stations with a negative trend. So despite the fact that the trends by themselves are not significant, there is a disparity between stations showing an increase in heavy precipitation, both in intensity and in frequency, than stations showing a decrease, both in intensity and frequency. So we do know that, the observations indicated that where we have stations, where we have data, where we have good data, there is a tendency to increase extreme events at the daily precipitation. I said where we have data because you can see that actually those maps, the two maps down here, show the stations that we have, and you see that there is a huge disparity. I mean, the stations are not homogeneous, and there are huge portions of the globe where we do not have any data. We have data essentially in North America, Eurasia, the tip of South Africa, and that's it, more or less. So we have very few stations elsewhere. We don't have stations over the oceans, of course. We have very, very few data. So data are not covering the globe, but where we have data, where we have a good data, there is an indication of the fact that extreme precipitations are increasing in more places than when they are decreasing. How do we relate this to global warming? We know converting PDF to PowerPoint doesn't work very well because the equations in particular got mixed up. But because I'm sure that you all know Pasquero equation that relates the saturation vapor pressure to temperature. We know that the saturation vapor pressure increases with temperature, increases non-linearly with temperature, meaning that at higher temperatures, the saturation value of vapor pressure is significantly higher. And clearly, the saturation vapor pressure is what determines whether we have a net evaporation or net condensation. Depending on the fact that the atmosphere has more or less moisture than saturation, we will have net evaporation or net condensation. So if the saturation vapor pressure increases, also the evaporative rate from the oceans will increase. And so the actual moisture that there is in the atmosphere will increase as well. What is shown in this map, in this time series, is the change in temperature in blue and in moisture in red over the last 40 years or so, 50 years actually, over the last 50 years. That's from the station data, from observations. And you can see that moisture and temperature really go hand in hand, not only in the mean trend, but also in the annual variability. They really go together. So that means that global warming determines also a global moistening of the atmosphere. And this is actually not a small signal, because you have to imagine that every couple of liters of water, a big bottle of water present in the atmosphere, we've been adding like a glass of water. So it's not a negligible change. There is the atmosphere, the air is much moister than what it used to be. And those are the stations that have been used in order to get these time series, which are, again, the stations that where we have data. It's not global. It's mostly over continents, of course, but that's the data that we have. And it says that specific humidity, which is a measure of moisture in the air, has been increasing. And when the air holds more moisture, also precipitations increase. So the top time series shows the rainfall, the total rainfall. Clearly, this cannot come from individual observations because I told you that we don't have a global coverage, so it has to come from a combination of observations and the model. And it shows that there has been an increase. Actually, from what we understand, the increase in precipitation doesn't scale in the same way as the increase of moisture with temperature. So moisture increases more or less with Clausius-Clapeyron relationship. So it's like 7% per degree of warming, whereas precipitation increases, but a little bit, scaling a little bit less. And that's because of changes in the circulation as well. But let's not go too much into the details. Total rainfall is increasing, has been increasing because the atmosphere has more moisture because there is larger evaporation. And now let's go to extreme rainfall. And here we can use station data. We don't need a model because we are essentially scaling everything with respect to the stations that we have. And also the daily time scale, there has been an increase in extreme rainfall, as shown in the upper graph, and I highlighted peaks that appear both in the surface temperature anomaly, specific humidity anomaly, and in the occurrence of those extreme events. So not only there is an uprising trend, which is what we were discussing in the very first slide, extreme precipitations have been increasing. So there is a positive trend, but there is also a correspondence. The years in which the globe is warmer are years in which the atmosphere is moisture, and those are years in which the extreme precipitations are more intense or more frequent. So this is kind of trivial, if we wish, because if we want, because it's saying we increase temperature, we increase the moisture in the atmosphere. When it rains more. That's it. But then it might be at odds, looking at the fact that also droughts, we hear that they are increasing. And so what is the relationship? Those two things might seem to be contradictory one to another. I said that there is more moisture. Okay, I can accept that there are more intense precipitations, more extreme events, but why should we also have more droughts? Well, let me first say that the signal on droughts is still under debate. First of all, we need to decide how to measure drought. And there are many different indicators, many different metrics that we can use. One, for instance, is the number of consecutive dry days. Or we could use a sort of a standardized precipitation index, which is a measure of how much it's raining over a specific amount of time, or the standardized precipitation evaporation index that also accounts for the evaporative rate from the soil. And so it's more a measure of the drought with respect to the soil moisture, how much water there is over the continents. In any case, the data are showing in some cases, in some regions, increase in droughts, in other regions, a decrease in droughts. So there is a certainly large variability. There seem to be regions, especially where we live here, the Mediterranean, where the droughts have been increasing. So lots of regional changes, but before going into the regional changes, let's stay at the global level for another minute. So I told you that there is more moisture in the air, but that's not enough in order to have precipitation, because clearly, in order to have precipitation, we certainly need to have clouds. And to have clouds, it means that the air must be supersaturated, so it must be above the saturation level. We measure whether we are above or below the saturation using relative humidity, which is exactly the ratio between the moisture in the air to the moisture at saturation. So 100% would be a saturated atmosphere. Below 100%, so if the ratio is below 1, then would be undersaturated. If the ratio is above 1, it would be supersaturated. The atmosphere typically is subsaturated. taking the global mean and long-term mean, is subsaturated, of course. But clearly, we can reach saturation, formation of clouds. So what does this ratio depend upon? I said that it's a ratio between the moisture that there is in the air, and what does this depend upon? We can think about it and think, well, it depends on the temperature of the water bodies that are evaporating. So how much water I have depends on the temperature of these 70% of the oceans, of the globe, sorry, that are covered by oceans. Evaporation mostly occurs over the oceans. And so the amount of water that evaporates depends on the sea surface temperature, essentially. And how much water the air can hold, so the saturation value, depends actually on the temperature of the air at the location that I'm considering. And considering that we live on continents, we are interested in knowing relative humidity over continents and precipitation over continents. And so the saturation value depends on the temperature of the air over the continents. The air temperature, the atmosphere is warmed from below. It's really transparent to solar radiation, so it receives energy from the ground. And so the air temperature will depend on the boundary condition at the surface, so on the temperature of the soil of the continent. And I told you already a few slides ago that continents are warming at a faster pace than ocean. What I told you now is that the numerator, apologies for the fact that you cannot really read the equations, but relative humidity is the ratio. At the numerator, we have the moisture in the air that depends, we said, on ocean temperature. At the denominator, we have the moisture saturation that depends on continental temperature. So the numerator scale as sea surface temperature, denominator scales as continental temperature. And I told you that the oceans are warming at a slower pace than the continents. So the numerator is increasing, but at a slower pace with respect to the denominator. So that means that the ratio is relative humidity over the continent is decreasing. And indeed, this is the bottom line here. Over there, you see the near surface air temperature increase over land in brown and in blue over the ocean. And you can see the different warming rate. And at the same time, we have the relative humidity anomaly. We see the decrease in relative humidity over the continents. We are not saying anything about the oceans, but in the end, we are interested on the precipitation on the continents, not really over the oceans. And so relative humidity over the continent has been decreasing, not very much, but has been decreasing. That means it is more difficult to get to the saturation value and get to the condensation, formation of clouds, and eventually precipitation. Not only that, there is also the fact that if relative humidity decreases, it means that the evaporative rate over the continent increases. It is more undersaturated, and so the evaporative loss of the soil increases. In the end, we get soils get drier and drier because of more evaporation, and because of there can be less precipitation. And actually, if we go to, oh yeah, I was forgetting another thing. I told you already that land and oceans are warming at a different pace. And we often think that this is related to the fact that the oceans have a larger heat capacity with respect to soil, large effective heat capacity with respect to soil, meaning that if there is a given energy input into the ocean, the change in temperature is smaller than if the same energy is put into the soil. This is true, certainly. This is mainly due to the fact that the oceans are fluid, whereas the soil is solid. And so the heat fluxes at the surface get distributed over a relatively thin layer in the soil. But actually, the possibility of having motion of the water and mixing makes the layer over the ocean over which the heat is redistributed much deeper than the soil. So you think about the mixed layer in the ocean, the layer which is stirred by the winds. And so the mass of water over which the heat fluxes are redistributed is much larger than the mass of soil over which the heat fluxes over the continents are redistributed. So that's certainly an important thing, but that's not enough, actually. The major reason for having a different temperature increase over the continents and over the ocean is due to the fact that part of the energy that's entering at the surface goes into so-called sensible heat, into conduction and increase of temperature, but another part that can go in evaporation, clearly in latent heat of evaporation. And clearly, over the ocean, most of the energy, lots of the energy goes into evaporation, and just a small portion goes into heating. Whereas over the continents that are drier, there's not a full availability of water in the soil. So there is less evaporation, and more of the energy actually goes into warming. So the enthalpy change, which accounts for both the sensible and the latent heat change, are very, very similar. And that's what is shown in this plot here. Moist static energy is essentially what I told you, the enthalpy. It's temperature change plus the evaporation, the evaporative latent heat change. You can see that if you sum them together for ocean and land, they go hand in hand. They are very, very similar. But the temperature change, as I said, up there is different because over the ocean, most of the energy at the surface goes into evaporation. So that's a major difference that differentiates the warming of land and of the ocean. So clearly we are talking about droughts, and I think it's quite interesting to focus on the drought that we've been having over the last year and a half, more or less, in Italy. Right now it's raining here, where we are right now. We're holding these PLANCKS in Milan. The last year drought has been a severe drought, and just a few weeks ago, a paper, an attribution paper, explained what can be the signal. I mean, what portion of the signal can be related to the climate change? What is shown in the upper left panel is essentially the pressure anomaly over 9 months from December 2021 to August 2022. That have been 9 months extremely dry, very, very dry, meaning that there was a very, very little precipitation. And what is shown in there, sort of the high pressure, what's red indicates the high pressure system. So it was a sort of an anticyclone, high pressure system, compared to what is the typical condition over those 9 months. And at the same time, the standardized precipitation index, which is one of the measure of droughts, was here, indicating that the actually focus on the little box, the green box over northern Italy. There was this index was very negative, meaning that precipitation and evaporation led to a severe droughts. And actually, these index is shown here as a function of time for the little box over northern Italy, and you can see that starting from the 1950s to today, there is already, you can see it by eye, the tendency to go towards a negative index, meaning that more droughts. Droughts are becoming more, I mean, the standard precipitation evaporation index is getting more negative, so more droughts. And clearly, one would like to know whether this signal is due to merely internal variability or whether there is a role played by the changing climate. So one of the possible ways in order to answer to this question is look for analogs of this circulation pattern with the high pressure anomaly over Europe over the past, essentially. And so two time slices were taken. One is pre-industrial, and the other is the last 80 years, where we have direct measurements. I don't have a pointer, and there are lots of figures here, but I'm going to drive you through what I think is relevant here. So the second column refers to the pre-industrial climate from 1806 to 1915, and the third column is the last 80 years, starting in 1942. You might wonder where those data are coming from. Those are actually the reanalysis. It's basically a mixture of the observations that we have put together with a model of the atmosphere. Those are the same models that we used to make weather forecasts. And you try to find a solution that both obeys to the equations of motion, but it also fits with the observations. So in the end, in the reanalysis, we have a sort of the best representation of the atmospheric state, starting from the observations that we have and using the physics that we know about the system. So you can see in those two columns the typical conditions that we have when the atmosphere was in a state similar to the one of last year, essentially. So the best analogs are found for each period. And the top row indicates the high pressure anomaly. And you already see that, and actually the fourth column shows the change. And you can see that the high pressure became stronger, essentially, wider and stronger. The high pressure region extended more into the Atlantic, and the intensity got stronger. We also see that the temperature, which is the second row, increased. Yeah, we know there is global warming, so not a big surprise, but actually it increased by much more than the global warming signal, than the global mean average. So meaning that during those events, Europe has been substantially warmer, more than what you can just expect from the global trend, the global mean trend. And the precipitation rate is what is shown in the last plot, in the last row, sorry. And also precipitation decreased. Red over there means drier, less precipitation. So by comparing those analogs, with excluding last year, because of course you want to keep that out of the analysis, otherwise the results might be impacted by that specific extreme. But by comparing the analogs, we might say that actually the frequency of those events hasn't changed, but the intensity of them has changed because of a bigger pressure anomaly. And what does the pressure anomaly do? I actually put it here. It's very, very simple to understand. Wherever you have a high pressure at the surface, high pressure means that the air is moved away from the center. There is high pressure, so the air is moved towards lower pressure, so it goes away. This causes surface divergence. Surface divergence by conservation of mass means that air must be subsiding, moving downward. And by moving downward, the air mass is found at higher and higher pressure. There is a warming, clearly, and if you had any cloud, those clouds would evaporate. So this big blob of warm air, high pressure at the surface generates the disappearance of the clouds because of the subsidence of the air, the removal, the divergence of the air at the surface. So this creates sort of a big mass of air cloud-free. And so that's the key in order not to have clouds, therefore precipitation. So in the end, the outcome of this attribution study is that climate change plays a role in the occurrence of last year drought. Let's move to some completely different extremes. I told you heavy precipitations are increasing, droughts might be increasing as well. Those seem to be contradictory, but we kind of reconcile them by looking at the physics. And again, also for temperature extremes, we can be tempted to say that, well, global warming, we expect warmer temperatures. So when we get really cold spells, we might ask, and actually some people actually tweet and ask everyone, where is global warming when those cold spells happen? And actually, those are quotes, tweets from Donald Trump. Years ago, it's snowing and freezing in New York City. What the hell ever happened to global warming? Considering that an individual cold spell is actually in contradiction with global warming. And actually, but those are not, I mean, just this very morning, I saw some other tweets referring to the drought that we had last year, and we are still in the sense that the system hasn't really refueled all the water that it didn't receive over the last year and a half or so. But actually, these days are wet and are cold. And so this very morning, there was this tweet saying, cold and rainy May. So what are we talking about? Why should we talk about global warming? So clearly, those are two completely different things, because global warming is, we know it's climatic signal, so it's a long-term signal, whereas the day-by-day variability is the meteorological condition and has not much to do with the long-term trend. But actually, there seems to be, well, we do know that warm events are increasing. There's no doubt about that. But there seems to be in the mid-latitudes also an increase in the cold spells. This is still debated. It's not clear whether the winter mid-latitudes are getting more and more cold spells or not, because many different people will give you different interpretation of the data, will rely upon slightly different data sets and would lead to different conclusions. But over the last 10 years or so, there has been a lot of attention with respect to how can those cold spells change in a global warming, in a climate change period. And so in order to understand this, in order to answer to this question, we need to know that in our latitudes, in the mid-latitudes, we get cold spells during the winter when polar air is able to reach our latitude. We know that polar air is really, really, really cold. And if it stays over the pole, it stays there. But once in a while, it's able to flow to lower latitudes. When does this happen? Well, the typical conditions for the winter conditions are that there is in the stratosphere, so 15, 20 kilometers above our head, there is a strong jet flowing from west to east. You can imagine as a river of air that's flowing very fast. And that's actually confining the polar air over the pole. And it's high up in the stratosphere, but it also affects the troposphere where weather patterns occur. If this is stable, this polar air is really confined to the pole, but it happens once in a while that it starts meandering, as depicted in the right-hand side. And when those meanders happen, there is cold air that typically sits in the high latitudes, able to reach lower latitudes. And if you have a wavy pattern, clearly you also have warm air entering towards higher latitudes. So at the same time, you might have a very warm condition at a given longitude and very cold condition at a different longitude, at the same latitude. So lots of longitudinal variability. And so the question becomes, have this occurrence of the waviness, of the wavy pattern changed over the past, and what does it depend upon? As for rivers, meanders form when the river doesn't flow too strong, of course. So if you imagine a stream down the mountains, the flow is I mean, the change in potential temperature is a lot. So the water moves fast, and the stream doesn't meander. But when you get to flatlands, the velocity starts going down and the river starts making meanders, of course. So the first thing is same thing. The strength of the jet is what determines whether you're gonna have a wavy pattern or not. And the strength of the jet depends upon the temperature difference between the low latitudes and the high latitudes. And so lots of attention has been devoted to the fact that there is this Arctic amplification. I showed you before that the Arctic is warming at a much faster pace than the global mean. So that means that the temperature difference between equator and pole is decreasing. And this might lead to a weakened jet stream. So there was a lot of attention with respect to this 10 years ago, and then people realized it doesn't work like that at all. So it's not because of polar amplification of climate change that this jet is getting waver, and there must be something else. And the something else, people now, yeah, let me skip this one. Look at it in the fact that well, let me go here. Let's say here. The waviness certainly depends on the strength of the jet, but also depends on the longitudinal on the surface characteristics. We are not living on an aquaplanet. The planet is not uniform. There are at the surface, there are lands, continents, and seas that are changing its temperature in a different way. And this means that there is a forcing coming from the surface that's directly generating meanders. So it might be this longitudinal change in the surface condition that's driving the waviness. And that's actually the direction in which the research, the frontier, is going in order to find the link between cold spells and global warming. The fact that the North Pacific, for instance, is differentially warming with respect to the rest might actually increase the waviness of the pattern and therefore favor the occurrence of cold spells, especially over North America, which is just downstream of the Pacific, of the North Pacific. But again, as I said, this is the frontier research, and there is no consensus yet. But I want to show it to show you that this is not, I mean, the increase in cold spells might not be contradictory with the idea that the globe is warming as a whole. There are many different processes that might alter these. I mean, one thing is to talk about the global mean change, another thing is about talking about variability with respect to the global mean change, and actually they can go in different directions. Heat waves are, I already mentioned the fact that, yeah, temperature, that's a very clear signal. High temperatures have increased, and heat waves have increased at the same time. Heat waves are typically associated with high pressure anomalies. I already told you before that high pressure anomaly means that there is subsiding air. Air is coming from top of the troposphere down towards the surface because there is divergence of the flow at the surface. So this means that the subsiding air finds itself at a higher pressure, it warms, and therefore, if there were clouds, they evaporate. So clearly, high pressure means disappearance of clouds, clear sky. And if you remove clouds during the summertime, that means that more solar radiation can reach the ground. And so there is more solar radiation reaching the surface and more warming. So high pressure means no clouds. During the summertime, that means warming at the surface. And actually, there is also a feedback at play because if you have lots of radiation reaching the surface, that means that if there was evaporation in the soil, that water would evaporate. And when you have a dry soil at that point, all the energy goes into increased temperature and it doesn't go anymore into latent heat of evaporation. And so the temperature increases even more. And so it becomes a positive feedback. I put this slide to mention that overall, over the globe, if you remove entirely the clouds, the planet would cool. So the net effect of clouds is a cooling. Wait, what did I say? I said the opposite. Sorry. The presence of clouds actually cools the planet because it actually reflects. Clouds are white. When you fly on an airplane, you see the top of the clouds is white. That means that the solar radiation bounces back. And so the presence of clouds is actually reduces the solar radiation that reaches the ground. We know then that today, which is cloudy, it was cloudy before, I don't know anymore. It's dark in here, and so I don't know. But we actually know that at this time of the year, if there are clouds, it's colder. If there are no clouds, immediately we get more solar radiation and so warmer. But this is an effect that's typical of this period of the year. We are in May. We are close to the solstitium, summer solstitium. And that means that we have lots of solar radiation, lots of solar radiation. If instead you think about the winter effect of clouds, is exactly the opposite. During winters, think about the night. A winter night, cloud-free, is extremely cold. It's a freezing night. Okay, so you see that in that case, there is no solar radiation. It's actually night. Doesn't matter whether it's summer or winter, but at night there is no solar radiation. So the only effect that clouds have is to reduce the radiative loss of long wave radiation emitted from the surface. So it's actually trapping the heat and keeping it. They work as a blanket over when there is no sun. So clouds can have those two competing effects. They reduce the solar radiation reaching the ground, but they also reduce the long wave radiation emitted from the surface and escaping to the outer space. So depending on where they happen, when, the timing, and the type of clouds, so whether they are low clouds or high clouds, the effect of clouds can have contrasting effect. It can be both a warming or a cooling. And actually, clouds are the major source of uncertainty in the projections for climate, for the future evolution of climate. We do not know exactly what's going to happen to what type of clouds, and not knowing this means that it becomes difficult to project the evolution of climate. As I said, cloud can both have a negative effect or a positive effect on radiation. But in any case, the presence of the heat waves is associated with the disappearance of clouds during the summer, because during the summer, the shortwave radiation effect is the dominating one. Okay, so I gave you examples of how contrasting signals might be reconciled thinking about climate change. Let's see what are the observed and expected changes in climate extreme. And the second column, the first column is just the event type. Then we have the second column, what has been observed starting from 1950 when we have reliable data. Then there is attribution of those changes, and then projections at different levels of global warming. The colors in this map refer to how likely the signal are, essentially, what are the probability that those things happened or will happen. And you see that the first two rows are deeply red, meaning virtually certain. It's virtually certain that warm and hot extremes, both in frequency and intensity, have increased at the global level, and that's due to the increase in greenhouse gases, and this will continue to happen. Also, cold extremes at the global level, not at a regional level, but at the global level, they've been decreasing, sorry, so the minimum temperature have been increasing. As we saw before, different portions of the world might have different responses. And then if you go to heavy precipitation events, over majority of land regions with good observational coverage, they have increased, and that's what we discussed. Let's not go through all of them, but we didn't talk about tropical cyclones. We mentioned the compound events, co-occurrent heat waves and drought, because we saw that there are feedbacks between heat waves and droughts, and those have an increase in frequency. You can see the others, but we can stop here. Actually, the droughts itself, agricultural and ecological droughts, the frequency, we don't have lots of confidence. They have increased in some regions, medium confidence, not a very strong signal. There are expectations that there will be an increasing drought in times to come. But as I said, there are still things that we do not understand, and the projections depend on many feedbacks that we do not understand. Actually, I put here just a couple of questions. So one is related to the presence of clouds that I already mentioned. This is the equilibrium climate sensitivity. It means if we double CO2, what kind of change in temperature, in global mean temperature, do we expect? And you see that we expect a change in between 2 to 6 degrees for doubling of CO2 with respect to pre-industrial levels. Actually, the blue and the red refers, I mean, the orange, the blue dots and the orange dots refers to the orange dots are the climate models that we use nowadays, the state-of-the-art climate models. The blue ones are a decade older, and you see that actually not much changed in the spread of the different equilibrium climate sensitivity obtained actually increased. So there are lots of uncertainties in those projections. Well, everyone agrees that doubling CO2 increases the global mean temperature, but narrowing the climate sensitivity has been challenging. We haven't been successful. And the major source of uncertainty really comes from cloud representation in the models because of the reasons I mentioned. Clouds, I mean, increasing or decreasing clouds depending on when, where, and at what level of the atmosphere it's occurring has contrasting effects. And then there are also other effects, more local, that makes things complicated. Thinking about the heavy rainfalls that I already mentioned, there has been the observation of the fact that the intensity and the frequency of heavy rainfalls has increased more in urbanized areas than in non-urbanized areas. So there might also be a local change that contributes to the signal. Not only the global change, but local changes might actually play a significant role. So extreme events, in several extreme events are increasing. This is actually a slide that summarizes the natural disasters that occurred. Those are data that come from reinsurance companies. Reinsurance companies are companies that insure insurance companies. They really, so basically when an insurance company has to pay a lot because a disaster occurred, reinsurance companies are those that give the money to the insurance company in order to avoid that they fail. So they are very interested in knowing how those big disasters occur because that's when they have to enter into the game, essentially. Unfortunately, they stopped releasing data set. Their data set was publicly available until 4 years ago or so, and lately they decided that it's no longer public. So those the numbers that I give you are kind of outdated in the sense that they do not contain the last years. But you can see that the natural disasters, they are differentiated between geophysical events like earthquakes in red, meteorological events, hydrological events, floods and landslides in blue, and climatological events like droughts and heat waves in orange. So the number of those events is what is shown in the upper left corner. And you see that the number is most of the natural disasters are related to meteorological events and hydrological events. But if you look at the fatalities, actually most are related to earthquakes. When there is a big earthquake, there's a huge number of fatalities, and that's what you see here. But for economic losses, actually meteorological events are really, really important. And so those events, so here remove the geological ones, remove earthquakes and volcanoes, and just look at the number of those meteoclimatic events that were important enough for them to mark them on their data set. You see from the 1980 to 2018, that's when they stopped releasing those data, the number of those events has increased by a factor of 3 at least. So a huge increase in the number of catastrophic meteoclimatic events. We are talking about climate change, so we might be tempted to think that this is due to an increase in the number of extreme events, but we have to think about, oh, sorry, I forgot to, this is written in Italian, apologies for that. But in order to make a disaster, you really need not only the extreme event, but you also need other ingredients. And we can think about them as the three ingredients, and using the tale of the bad wolf and the three pigs. You know that the bad wolf wants to eat the three pigs, and the three pigs build houses. So clearly, the bad wolf, if he's able with his breath, just by blowing, he's able to destroy houses. It means that he has an extreme capability of blowing. So the extreme metaclimatic event would be the wolf blowing very, very strongly. But if he blows where there is nothing, nothing happens. So the extreme event per se doesn't generate any disaster. It's just blowing strongly. Clearly, in order to have the disaster, you also need something exposed to the extreme event. So the house has to be in front of the wolf blowing his monstrous way of blowing. So exposure. And finally, if the house has been built by the clever pig, nothing would happen. But if it has been built by the lazy pig, then the house will be destroyed. So three ingredients are extreme event, exposure, and vulnerability. So there are three ingredients, and actually the threefold increase in the natural disaster, in the number of disasters, are not due to the increase in the extreme events, in the blowing, but are largely due to the increase in exposure, because over those years there has been economic growth, demographic growth, so more things are exposed, certainly, more people are exposed, and there has also been, in some cases, an increase in vulnerability. And that's where we have to really pay attention in order not to be too vulnerable. So there are many, many things that are coming together. Let me jump to the conclusions, which I decided to leave blank because I would like each one of you to draw its own conclusion, his or her own conclusions. What I think I showed you is the fact that there are things that seem to be contradictory, and instead they can be reconciled by understanding the physics behind it. We are living in a time of climate change, and certainly our exposure to major climatic extreme is changing. We know that the human beings are able to live in very different climates, but we need to get ready. We need to get prepared for that, because a city built in Chicago is very different from a city built in Beirut, for instance. I mean, if there is a different climate, there is also different infrastructure building and such. So we have to adjust our societies, certainly. And we also have clearly to limit our vulnerability. And I think this really comes from having a better connection with the world around us. So being less vulnerable means knowing what we can expect, respect more the variability without thinking too much that we can do whatever we want because we are able to tame whatever. No, we are not able to tame whatever happens. There are things that happen, and we just have to be aware of what can happen. Clearly, that doesn't mean that we don't need to do anything for climate change. Of course, we also have. I mean, it's the other face of the same coin. We have to live without thinking that the world can give us anything and that the resources are infinite. I mean, climate change is just one aspect of a relationship that we kind of are doing wrongly with the environment by thinking that the resources are unlimited and that essentially we can do whatever we want and we will always be able to extract all what we want. We've been living in a time in which this was happening. We were discovering new ways of extracting energy, extracting food, extracting more. And we kind of thought that, okay, this can happen forever. I think this has to be changed in terms of realizing that things are not infinite and so be more respectful. But I really think that being more respectful comes naturally if we are able to look and meet with the environment around us, um, and be more in contact with it. So whenever some people ask me, what can we do? I mean, I'm not an expert of CO2 reduction and such because I study the climate dynamics. But the very first thing that I think is stay outside, connect to the world, because that's a way of uh, knowing, loving, and respecting. Thank you.
Thank you. Thank you, Professor, for this amazing talk. We have time for just one question because we are late. Here there's a question. Wait. We have the microphone.
Thank you for such an inspiring talk. So I was wondering, when you compare the data, for example, for the extreme rainfall events with the data for the increase in global temperature or local temperature, and of course, you know that causation is not that correlation is not always causation. So what kind of analysis do you do in climate science to show this? For example, do you make some projections based on the increase in temperature to show that this trend in the increase of extreme events will follow it?
Yeah, absolutely. You can certainly do, clearly you build a model and then you want to see whether it works or not. And so you make predictions and you see whether it works or not. But more important than that, even I think it's the understanding of the physical processes, and it's a fun part of being physicists, right? So you want to understand what the processes are, and then clearly you need to verify. But first of all, you want to not just look at correlation, because clearly that is suggesting of something, but you want to know and to link the dots in order to make a story. So you want to understand the physical process, and then you make that's how science works. You do an experiment, you make a prediction based on the results of that experiment, and you test it again. Now, the climate system doesn't allow us to do repeated experiments, and so how does climate science can call itself science, even without having multiple Earths on which to do the same kind of experiments over and over? There are many different ways. One is certainly, as you said, making prediction based. Okay, one is building a model of your system and use that to repeat. Clearly, to repeat experiments essentially, do the experiments many times. Clearly, you would not know for sure that your model is correct. So you always have to make sure, and actually, we know that our models are not perfect, of course, and so the models are always improving. A way of knowing whether the models are going the right direction or not is to use the past climates that were very, very different from our climate. The Earth has been going through huge changes in climate. There have been crocodiles in Greenland, for instance, or there have been times in which the Earth was a snowball. So very different climates, and you would like your model to be able to recreate, reproduce, and to fit the data that we have from those times. So you would know that under very different climate conditions, the model works, kind of, I mean, at least is reasonable, does reasonable things. This is not yet completely done. So going very far from the actual climate system that we have right now, it's not something that we can do very easily. So there is lots more work.
Thank you.
Thank you again, Professor. You have to know that we always go with Claudia Pasquero. We already had two lectures with her as highs because we always know that it's sure that the talk is inspiring. So thank you again. We have
Thank you.
no, wait, please. We have a little gift for you because it is always a pleasure to have you. So.
Thank you. Thank you.
The usual photographs. And also
Thanks a lot.
a bottle of wine, of Italian wine.
That's always welcome. Thank you.
Yeah.
Thanks a lot.
You're welcome. Pictures, usual pictures. Thank you again.
Thank you.
Thank you. Okay, we are just 5 minutes late, and so I would like to tell you that before our next lecture, we have a little surprise for you.
So, dear students of the, how is it called, World Physics Olympics, PLANCKS, I congratulate you that you are there in Milano and you have your competition. I understand there are about 50 groups from many different countries. I just want to mention physics is fun. Physics is extremely interesting. Follow your nose. Any problem in physics is rewarding when you go deep enough, when you really analyze what's going on and what's behind the scenes. And to do this for part-time of your life or for all of your life, it can be extremely nice, and I'm sure you will enjoy it. All the best and good luck to everyone.
Anton Zeilinger, the Nobel Prize of this year. From a Nobel Prize to another Nobel Prize. He is the Jacksonian Professor of Natural Philosophy of the University of Cambridge, where he is also the Fellow of Trinity College and professor also at the University of Geneva. He was awarded of the Nobel Prize in 2019 for the discovery of one exoplanet orbiting a solar-type star. Please welcome Didier Queloz.
Thank
The
you.
stage is yours.
Thank you very much for working. Like, fantastic. Thank you. Well, first, congratulations to you who are in this amazing event. I'm quite excited to be here. I was remotely to the previous one, so I'm very glad to have a chance to see you. I think this is really great to be in this event. Why is it great? Because you're the future of physics. So I do a lot of mentoring, trying to explain what is to be a physicist, and that's a great place to be. What I would like to share with you is certainly one of this new field, very exciting, that goes much bigger than the physics only. But physics is the starting for many different fields, so in a sense that fits very perfectly the purpose here. So we'll be talking about exoplanets. You may, well, I think you're all too young to know what was before. We were looking for planets, so you were born with essentially the idea that there are planets under the stars. And what I want to try to explain to you what's going to happen next, you are going to experience is this looking for life as part of the questions where there is life. Certainly open-ended question here. Okay, so let's start. First, let's start with the astrophysical context we're talking about here. What do we care about planets? So that was a very old question from the beginning of the quest 30, 50 years ago. I think what you have to understand here, if you look at the global scheme of things, let's say you make the universe, and it's a very exciting but very boring event, because at that time you create essentially time, space, matter. But matter, very limited. It's only hydrogen, essentially a bit of helium and a bit of lithium, so not very much. So extremely boring, leaving aside the unknown of the dark matter here. So what is going to happen is that something great called a star, which is a machinery that is producing the chemistry. All the chemical elements are being produced thanks to the star. And you think about this, the fact that you have stars that doesn't come right away, it takes some time in the history of the universe, was already encrypted into the law of physics, and it had to happen. And then you end up with all these great elements. And then from these elements, if you reach a cooler temperature enough, which is unlikely in a star, it means either in the interstellar mediums or on something that we call planet, you start doing chemistry. So then you play with the chemistry, your molecular chemistry, and then you make life. So you see there is something quite interesting here, is this global connection between things. And this is just to remind you that when you're talking about planet, you're talking about something part of the great questions, which is really the unit of what you have into the universe, and a very exciting unit. There is other fascinating objects like black hole, but they are kind of end game for the complexity. And certainly they will be the end game of the universe at some point here. So what I will be dealing with is planetary systems. So something is quite simple, and I was already mentioned in the 18th centuries, and you can really understand that, is when you just take a cloud, which is of the order, or in that case, and 10 to the 6 to the 10 times larger than the solar system. So you're having a problem. The problem is the angular momentum. How do you fight the angular momentum? Technically you end up with something rotating super fast, and then because it's rotating too fast, you cannot make it, actually. So something has to get the angular momentum away here, and a trick that you can do to get away is making what we call a protoplanetary disk, and then with something that holds the angular momentum of the system. So if you can just do the computation, you can look at what is the angular momentum stored into the sun, which is huge, which is 1,000 times more mass than Jupiter, compared to the angular momentum which is stored into the orbital motion of Jupiter. And you will find out that the whole angular momentum is into the Jupiter area. So making planet is a way to get rid of the angular momentum. And that was mentioned in the 18th century already, 19th century actually, as the very foundation why there must be planet everywhere. Now, it took a long time to find this planet, because the reason why we were a bit obsessed by the solar system, and the only system we could imagine is the one we are in, with the small planet inside, the giant planet outside. And there has been a fantastic series of beautiful theory explaining that has been confirmed by probe that we've sent into some of these planets so far. And what happened 30 years ago is the first planet that was picked didn't fit into this kind of a grand scheme. It was a planet like Jupiter, but not at the right place. It was a planet next to the star, as you know. So how did that happen? I just want to go a little bit on the past to explain how you can really make such a discovery, how it happened. Well, the very principle to detect a planet is simple way. You look at the star and you try to find a trace of the planet happening. In that case, you see the motion of the star due to the orbit of the planet. So maybe you can pick this motion, usually the Doppler shift, which is what is pictured here by this wiggly wave going from red to blue, just the motion of the star. You look at the speed, change speed of the star. And if you're lucky, you can also have the star just crossing exactly now in front of the line of sight between the star and the telescope, and produce a blimp, and that's what you call a transit. The problem of these techniques is nobody was betting on that 30 years ago, for good reason, because when you look at the signal that is produced by the biggest planet producing the biggest signal in the solar system, which is Jupiter, it's a very tiny signal in terms of astronomical motions, very small, and was very challenging to make the machinery to detect that. Also, it takes forever, because you need to track the motion for more than 11 years, so it's a very long time program you want to do that. And if you look for a transit, the chance to pick up a transit is almost zero, because Jupiter is so far away that to get exactly aligned, your chances are almost marginal. So you need to observe really a lot of stars to find an event that lasts for just a couple of hours, in the case of Jupiter for a day, and that's it. So these both techniques were seen as non-relevant, because the solar system was seen as the archetype. Well, despite this, I got embarked into a program of doing my PhD to develop a completely revolutionary machine. That was, the purpose of this machine was to reach the level to detect Jupiter. So I want you to just go a little bit around that, because some of you may be building machine here just to understand why we made the breakthrough and what did happen. So first, you don't have to build an extraordinary machine with tons of physicists. Well, you do in some case, and if you want to look for the Higgs, you better be. But in some other case, there is plenty of stories where major discovery was made with small teams, but very agile and very creative. So we have been extremely creative at that time. We built that machine, which is now on display in Haute-Provence. If you go in Haute-Provence in south of France, you can see it, which is a spectrograph. So it's making it spread the light from the star. Spectrograph is something that Newton did in his room using a prism, so it's an old-fashioned idea. It moved to the star. The first spectrograph for stars was 100 years idea. So why this one is so special? Well, because we have implemented the spectrograph in a complete new way, and a lot of them right now are built exactly the same way. It's kind of the father or the mother, all the further spectrograph of that kind. The first idea, you need to spread the light with a very high resolutions in a very compact way. The design to do that is this big piece of optic you see, this big kind of rectangular, it's called a grating. We're the first one to use a very specific grating of that size, which is called an R4 echelle grating, that produce what you exactly need. Didn't exist before. They have another kind, and Elodie is the first, that's the name of the machine, is the first one using this grating. The second one is this kind of orange fiber you see on the right. For you, it would be on the left. That is conducting the light into the spectrograph. So it's quite common, everybody knows optical fibers these days. In the 90s, it was just barely, the optical fiber Nobel Prize was in the 70s, so the concept of optical fiber was already known, but it went into the infrared for the technology because of the communications, telecommunications, but it gradually moved to the visible. That became more interesting for us in astronomy. And in the 90s, the first kind of astronomic fiber were available, but how do you make them work in a way they are applicable to astronomy? That was really new, and that's what we did. So we managed to install optical fiber to contact the spectrograph. And that's a complete revolution, because before that, you have to have your machinery hanging behind the telescope. So you have to imagine during the night, the change of the temperature, the motion of the telescope. The whole optic is moving, is shaking, is changing temperature. It's very complicated to have something stable. So the fact you have an optical fiber connection to the machine was a way to make a very stable spectrograph somewhere in the basement, on the control environment, and it was the second big news. The third one is computer. So right now you have your computer on your cell phone, but in these days you have only two options. A crappy machine, which was based on MS-DOS or the previous Windows system on PC, that essentially could do only bureaucratic stuff, only editing text, not very much serious work, computing work, certainly a very limited 8 bits, so nothing really serious you could do with that. Or you go to the big machine, they were using that kind of space, and one of the big company at that time was Cray. You have heard about the Cray computers, but they are way too expensive and very difficult to get access to. Except that in the 90s, some of the people from these big companies that were producing a 30 bits computing unit left the big company and created a small company called Spark, or that become Sun Microsystems to just make them as a complete setup. It's called the Spark system. Microsoft Computer, they are, I think, gone right now. But they were the first supercomputer in a box we could use. And that was a complete revolution in the 90s for most of the physics lab that needed superpower next to them and not going connected to others. So we just had access. That was my baby when I started my PhD. And with that, we could compute the very complex solving problem, which is how do you deal with the speed? How do you compute the speed of the star with this machine? And that's why we made the discovery. No, we made the discovery was a big surprise, because the expectation was for me to start the program but not to detect anything, because it would take 10 years to see any change of a star due to an orbital motion of Jupiter. Well, it turns out that there is planet on short period. And that's what I found out. Really, I was shocked during my program when I was observing. I didn't expect that. So I thought everything was broken, didn't work, and I really had a challenging time. And even when we published Discovery, because most of the community was against us. It was too revolutionary, it was too strange, there's no way you could explain it. Well, in a way I survived, and it ended up having a Nobel Prize. This is the reason why we had this very, very creative element here. So that was the beginning. Now it's clear that 30 years later, we are in a completely different situation. So this is a kind of outlook where we know where we're sitting in terms of planet and other stars. So each dot here is a data point. It's the real data. We know either the mass of the star or the size, sorry, the mass of the planet, or the size of the planet, or the period of the planet. We know the mass from this motion, Doppler shift. There's a bit of a sine angle here, but we can just solve that. It's just a statistical problem. It's not very complicated to get the picture. It doesn't affect this diagram. Or the size comes directly from the transit. So you recognize on the very top, on the top left, all this massive Jupiter or massive mass on a short period. Look at the period here. We're talking about few days there and very massive. These are the hot Jupiters we're talking about. There has been detected, there's plenty that has been found, and they are sitting there in the diagram. We do have other Jupiter as well. They are on that side of the diagram here with maybe 5 days, 5 years, 6 years, some of them 10 years. But look at the log scale here. We're also detecting much more massive planets, 5 times Jupiter, 10 times Jupiter, 20 times Jupiter. Where do we stop? At some point, when you reach 80 times Jupiter, it becomes a star, because there is enough pressure to ignite the thermonuclear reactions at the very core of the object we're talking about. So there's a bit of an interesting game here. What are we talking about? But what was the big surprise in these recent discoveries is the fact that we have a whole unexpected number of planets which are on a short period. We call that the super Neptunes or super Earth. They are in this, on the size of the diagram in terms of size, they are there in terms of mass, they're ranging for a day to go around the star. So they're really grilled because they're so close to the star. You know, the shortest period, the closer you get to the star, up to objects which are farther down, up to 50, 60 days. So that was really a big surprise here to detect all this planet. And the other big surprise, there is no planet that seems to be similar to the Earth or Venus in this diagram at the very orbit of Earth or Venus. We do have Earth's mass, Earth's size, as you see it, but we don't have the orbit and the size at the same time. Why? Well, because the technology we're using, the techniques I described to you, are kind of limited. And this is the limit we are dealing with today. Some of them are difficult to fight, like the time. That's why there is not much hope to get transit for anything with a period more than, let's say, a year. It's very difficult. And then anything on the left you can find on this diagram, anything on the right you can't, at least not with the current program. We're battling, we're trying to fight this. It becomes a very tiny signal. You start to fight against the stellar instability, and this is why we don't have any. So if you're asking me right now how many of Earth-like systems we have, I tell you I don't know, because it sits into a region of the diagram I cannot. But I can tell you how many of the other systems we have found, and the number are quite impressive already, because we know that while there is very few hot Jupiter, they're very spectacular. There's very few, is few percent. So you look at a star, the chance to get one is few percent. But look at the number of this famous object called super Earth and many Neptunes. For 50 to 80% of stars have a planet like that. 50 to 80%. So this is the majority of the planet in the galaxies. They are not like the solar system. Solar system is already not the kind of archetype. And this is, if you have to remember one thing of this talk, that's one. So we have learned that. It took 30 years of program to find out. It's an interesting story, then it's a bit the same story that you go back 500 years ago, when you believe that the sun is orbiting the Earth. We tend to see ourselves in a very special position anytime. It's just a bias. It's a very common bias. Makes sense. I think it's also applicable for life. And we have to think about that. I'll come back on that. We have to be a little bit careful how we see ourselves here. So it's fascinating. It's luck or gift of nature, because the fact we have so many planets that turns out to be so easy to detect with a technique that was designed 30 years ago and not optimized for that, give you so many planets. And that's why I know it's a huge field and we have a lot of very interesting planets to study. Well, the good news as well is because the planets are on a short period, most of them are hot, but because they are too close to the star, but some of them are orbiting stars which are cooler than the sun. So if you consider a system like the solar system, but you take a star which has a mass, you decrease the mass by factor 2, for example, well, the temperature will go down quite a lot, quite substantially on the stars. You will end up with a star of 4,000 degrees. But because the illumination, you got to the power 4, and then you end up with far less irradiations. So it turns out that even if some of the system are close, like they have an orbit of 10 days, 20 days, which is shorter than the orbit of Mercury, you don't get a very hot planet because the star is cool. And there are some very interesting systems you can study and consider them as not really similar in the conditions that the solar system, but kind of a smaller scale version of it was changing the star. So the fact you have this bizarre planet doesn't prevent you to make some interesting comparison, also to look at a cool planet. Now, the other element here, you can combine the mass and the size and you end up with density. And that is also a very exciting territory. So these are real data. So the error bar is the uncertainty you get. I just have to help you to read it. I added a couple of planets that we know quite well. And I also added the kind of expectation between the mass and the radius you have according to the understanding of the nature of the planet. So on the top, we have the giant planet. It explains very well Saturn and Jupiter. They're well along this line. Most of the discover Jupiter, which are more likely hot Jupiter in that case, because that's where we really easily can get both the mass and the size, they are all sitting above it. It's a density diagram, so it means they are less density. That's why they're sitting above it. It's just kind of expected because they have a different temperature. There's a lot of different physics going on that can explain slightly inflated planet, while there are people debating exactly the origin of this. We do have some fitting along the line, but then there is something interesting for you to notice here is when you reach the mass of Neptune, the blue planet there, the model that we use to compute the density of Jupiter and Saturn doesn't work. It produces a much lighter planet, and there is a simple reason why. Essentially, the structure of Neptune is the same, but you remove the hydrogen of the planet. So Jupiter and Saturn are full of hydrogen because they managed to grasp all this gas at a stage when there were plenty. Neptune didn't, or maybe there were not enough hydrogen around where the planet was formed. It ended up something much more compact. This is why we have Neptunes. The blue line, it doesn't really exist in the nature. It's a planet that would be made only of water. Why do we make a planet of water? Because it turns out that we know very well the state equation of water. We know extremely well how water behaves on extremely high pressure. There is a rule diagram. If you're curious, you look on the internet, the rule diagram of ice water. You can produce ice at high temperature because our friends and colleagues in earth sciences needs this parametric value because that's the only way to study the internal and to predict the internal structure of the earth. It's to understand the water under high pressure. So this is why we're using it. And it should give you an idea, if you make a planet entirely of water, where it would sit. It doesn't really exist because planet has a structure. The heavy elements are sinking just due to the gravity at the inside, at the core of the planet, while the light elements are sitting outside. So we have this structure, but then we give you some ideas. So we have plenty of planets that's sitting within this regime. They are denser than Neptune, but they're not like a rocky planet, because a rocky planet would be the green line. The green line is the density of the Earth. 1,1 is where it's sitting the Earth. So we have a couple of planets that would qualify as rocky according to this density diagram. It's a bulk density or an average density, so it doesn't tell you anything about the structure. It doesn't tell you about the core mantle and ratio, we have no idea. But it's set into this regime, which is already interesting, that tell you the planet must be made of rocks. And then if you look at the diagram in more carefully, there is a kind of a lack of planet between the famous water planet and rocky planet. And this is the topic of a lot of excitement these days to understand how you make a planet like that and what is the story to build a planet. And this is ongoing today. We call that planetology or exoplanetology. So in that sense, the people studying at that level of detail, the planets, they were limited to the solar system. There's still a lot to do because you can study that in great detail. But technically, you have access then to an infinite number of planets right now under the stars. You can't study that in great detail, but you have access to the global diversities of the planet. And that is telling you the story. And not everything is understood, but that's what is happening today. So we do have a diversity of planets. How far could we learn more about the system? Well, the one way to learn more is to use this very special moment when the planet is transiting, has just the right orbit to transit in front of the star. So this moment of the transit, there is another moment as well, which is called the eclipse, when the planet is behind. You see the two options here. Planet is in front or planet is behind. We have a couple of fantastic equipment right now, some of them already operating, like the James Webb Telescope, other that are being built, like the extremely large telescope in Iso, Chile, and that big chunk has been produced by the Italian industries. All the mechanic part is produced by Italian industry here. And then Ariel, which is the next ESA space missions that's going to study the planet atmosphere. So the reason why here I mentioned that is when you have this event, you can study the outskirt of the planet, the so-called atmosphere of the planet. What do we care? Well, actually, there's a lot of information you can retrieve from the atmosphere, going for a giant planet or rocky planet, if there is an atmosphere. And if there is no atmosphere, you can already retrieve the surface element of the planet. How does it work? So I decided to give you a little bit of a 101 here on how does it work, to give you a feeling. So if you are in the ISS, you would look at this moment with a visible camera. You would see this beautiful blue planet, which is, and in that case, simulate a planet transiting something that, in that case, I put the moon just in the back just to have as a comparison here. What I would like you to focus on right now is when the moon connects to the atmosphere. You look at the moon atmosphere of the Earth connection, this tipping point over there. Well, you do realize first, and that's always good to remind you, that the exosphere on Earth is very tiny. It's about 10 to 20 kilometers. So the atmosphere of the Earth is really a kind of a very thin peel out of something which is 6,000 kilometers, right? So you're looking at something very tiny, and that's what you see here. You see the blue, which is essentially the Rayleigh scattering related to the fact that the blue just gets diffused everywhere. That makes a blue sky, and then the rest of the wavelengths continue to hit. And then we had this beautiful talk before explaining the connection between all the relation between the clouds, all the stuff here. Now, let's imagine I take the same picture at the same moment, the same camera, but I use another wavelength. So pay attention to the tip between the moon and this. This is what I would get. This is an infrared. So I go to the infrared, 8 micron in that case. 8 micron is a beautiful wavelength because you see through the atmosphere. Nothing is going to stop you. There is no water band. And you hit the surface of the planet. So you've seen the planet look a little bit smaller, right? With the 10 kilometers a bit bigger, right? It's a bit smaller. So when you do a transit, you measure actually the size of the object. If you measure in the visible, you will hit part of the atmosphere. It will look a little bit bigger. If you go in the infrared, it will be a bit smaller because you're hitting the ground. And I can try to hit the highest possible component in the atmosphere, and you all know what it is. This is the ozone. So it's very well known. It's 9.6 micron. The ozone is sitting about 50 kilometers above. This is where it began formed. As soon as it got down, it got destroyed and reformed again. So, and you see then the planet is huge, much bigger. Compare the infrared and the ozone. It's the same planet. We observe the same event with 2 different colors. One is 9.6 micron, the other one is 6 micron. So just to tell you that if you observe this transit event in different wavelengths, you will scan through the atmosphere depending on the molecule you're going to pick. So that's what the James Webb has been doing. There's this famous picture. It was done already 10 years ago. It's not something new, but this is just beautiful, the way it's being done, because of the size of the telescope right now. You see what's called the amount of light block, or the size of the planet, in a way, on the vertical axis. And the horizontal axis, you see the color, the wavelength, right? And you see ups and down. It means the planet doesn't have the same size depending at the color you're observing the planet. Now, the trick here is to try to understand that. It's kind of a complicated problem. It's called retrieval. It's how far could you match what you see with something you model? Well, you need an atmospheric model, you need to know the pressure, you need to know the temperature, you need to make some assumptions on the nature of the planet, and then you can turn the problem around. What is good if you have a lot of data, if you have a lot of wavelength, there is only one solution that would fit them all. So the more you have information, the more you can fit it in. In that case, there is a clear model on that planet, which is a hot Jupiter, by the way. It's not a rocky planet, it's a hot Jupiter, that demonstrates that there is plenty of water on the top of the atmosphere. It's not new, we had it already 10 years ago, but that's just well shown here. And actually what we do see is the planet is bigger when there is water. There is all these peaks at the time of the water, because the water is sitting above and is absorbing the specific wavelength you're seeing here. The other wavelength, there is no absorption from water, so it goes slightly below into the atmosphere until it's being absorbed by something else. And that's what you see here. So, short message, we can observe an atmosphere of a planet without really seeing the planet. By using this trick, we can analyze. It's a big planet, but nothing can prevent us to detect smaller ones. No, still the challenge is the number. A transit of Jupiter on a solar-type stars produce about 1% event. So a tiny blimp, a 1% decrease of temperature, right? That's a Jupiter. Now, the atmosphere of Jupiter is about 1% of the size of Jupiter. Like for the Earth is 6,000 kilometers. The atmosphere is 60 kilometers, the upper bound boundary. It's 1%. You can take this number if you're being asked. So if you want to see the effect of the atmosphere on the transiting planet, going back to the Jupiter example, it will be 1% or 1%, right? So 10 to the minus 4. This is what people are doing. This is what here you're seeing, 10 to the minus 4 effect. Now, if you go down to the Neptune planet, the transit will be 10 to the minus 3. Still, the atmosphere still 1%. So it will be 1% of 10 to the minus 3, 10 to the minus 5. Becomes a bit more challenging. It's still barely possible, and the James Webb Telescope will do it. So there will be, in the press, and it's already popping up, a series of direct detections of atmosphere of Neptune-sized planet. Now, let's go to the most difficult one, which is the Earth. So the transit of the Earth is still one order of magnitude below. The transit is a 10 to the minus 4 detections. Can be done, has been done. There is plenty of Earth-sized planets detected in transit. But now if you want to detect the atmosphere, it's 1% 10 to the minus 4, which is 10 to the minus 6, which is really not within the scope. It's the size of a dot here. So unfortunately, don't expect these techniques to give you anything specific, except if you change the size of the star. Because all what I did, the math I did here, is I assumed the star with the size of the sun. Now, I can give you a star smaller. The smallest I can give you is a star which is 10 times smaller, actually, which is called ultra-cool stars. It's 10 times smaller. So you shrink all this math, and then you end up where you have an Earth-sized planet transiting a low-mass star. One of them you may know is TRAPPIST. You may have heard this name. In that case, if the atmosphere is 1%, the effect is 10 to the minus 5, and this can be done. So in the next 10 years, you may be hearing about these techniques, the similar diagram, on a planet like the Earth. Just want to share this with you. Now, the second thing you can do as well is way more than that. You can observe the system during the whole, orbits. You take a telescope, you point to a transiting system, this is what you get. So you get the moment, it's called phase 0, it's the orbit phase, it's just you wrap up the orbit of the planet, the transit. You have this dip. We've been talking about that. So this is the whole idea of transit spectroscopy. But you have these two moments where you have the second, you have the time here, and then we have the eclipse when the planet is behind. The planet is behind. It means that's the only moment when you only see the star, right? So this corresponds to the amount of light that comes from the star, right? Now all the rest, what is it? It's a planet. So anything which is above this yellow line comes from the planet. Again, you don't need to see the planet. You can see a mix of the two if you know exactly where is your 0 point here. And the 0 point is at the time when your planet is behind. So you use this, and this is typically what you expect. It's called a phase function. You have that with the moon. You see it every time. The moment when the planet show you the dark phase, it's dark phase. When the one phase of the planet is shine, and you see just the other side, which is the time of the transit. And then you have the other side, when the planet is about to get behind, it's a dead side. And then you see the direct line shining or reflecting directly from the planet. I show you that because you can do whatever you want with this. You can study in any wavelength you want. You can study with any spectroscopic tools. So you can detect the motion of the speed of the cloud. You can detect the nature of the cloud. You can study some level of the surface of the planet, if you can see down to the surface of the planet. It's as far as you can access to. If you observe a planet like Venus, you will only see the upper deck. You will not really understand very much the bottom of it. If you observe a planet like Mars, you will essentially access the very surface of the planet and all the thermal emissions or reflection, depending exactly the nature of the flux beaming in and reflecting out from the planet. It's super powerful, and you can combine all this together. So the short message here is people are talking about direct imaging of planet, and it's going to happen certainly in 50 years. There will be plenty of new technology, moon base and big spacecraft doing that, but you don't need to wait for that. The creativity is quite alive in this, and you can use this trick or this transiting planet to do that. The good news is there is systematic search for that kind of system. The first one was the Corot mission, then the Kepler missions, and then followed by the TESS mission. You heard about that. There's a Swiss satellite, Swiss-European satellite. It's called Cheops flying as well, and there will be Plato later on. So there's a lot of mission right now, which is scanning the sky to find all these systems for this very reason then. So I hope I convince you, then we can study then the atmosphere of a planet without really seeing it. So let's continue moving then forwards and try to push a little bit to the future here. What about the Earth? So to understand the Earth, I have to show you the Earth stories. So this is a famous diagram if you study Earth science and physics of the Earth that you will see one day, or you may have seen it already. This is the story of the Earth like a clock. You start at the bottom here, and to show you that the Earth as it is today has not been always like that. Depending on the time you look at the Earth, you end up with a very different kind of planet. When you start with the planet, there's a lot of gas that is gone right now, like hydrogen and helium. I mean, there's a lot of restructuring of the planet because the heavy element like iron, used to sink in because of just the weight and get inside. That's why you have an iron core and inside of the planet, and then the light element tend to be floating around due to buoyancy. They're just outside there. You have a kind of a magma planet. It's very hot. There's a lot of stuff falling, this stuff being cometary impact. This comet comes from the outside part of the solar system, which is full of carbon. Why? Because there's a lot of CO2 in a gaseous form that is embedded with the hydrogen at the beginning. Because the CO2, when you cool it enough, it becomes ice. You get a lot of sticking ice on comet outside the solar system. This is why when you bring a comet, water as well, water and CO2, this on comet. This is why when you bring a comet next to us, you see this beautiful tail, because the gas that used to be frost, because it's cold outside, is warm up, and then it used to be solid, then it's go back to the gaseous form, and this is what makes this beautiful tail. So you have a lot of carbon, so you never miss carbon on the planet for that reason. And then you cool down, you have a CO2 atmosphere, and then at some point something happens. It's called the prebiotic moment, when the chemistry on the surface of the planet produce life. And then life takes over, and takes over so much that start to produce another atmosphere. And in a sense, the atmosphere that you're breathing today is entirely the output, the outcome of life. So what you have, the oxygens, even the carbon we have, everything is processed and reprocessed by life. So we have a planet which is completely alive, completely embedded into life. So in that sense, it's a fascinating moment because you're connecting very dots together here, the very early astrophysical moment and everything. Now, what is interesting in terms of astronomy, if you ask the questions, what it looks like if you can't go, but if you could just look at a planet like that. And this is what you see on the right. You see 3 different moments of the history of the Earth translated into an astronomical form when you just look at it. And I don't want to go to the detail here. I just want to point, Archean Earth is before you have life. Proterozoic Earth is we have life, but it has not really had the time to develop this full amount of oxygen that you have right now, like modern Earth. The question is it a signal that is realistic to expect? So as a future physicist, there's something you should look at here, which would be striking to you. This is so different. I mean, whether you look at the Archean Earth or the Proterozoic Earth and modern Earth, they are completely different signals. You don't need to understand the detail of it. You don't need to go to the 3rd digit to find a tiny difference. It's blowing out your mind. It's obvious you have a different structure of the atmosphere here, which is related to the different atmosphere that you have in the planet. So I do pretend that there will be a moment that we will be doing that systematically on hundreds of planets that we will have found. It's just the beginning right now. I tend to think the beginning of that field as the beginning of when people started to break the atoms. And Rutherford in his lab 100 years ago was breaking the atoms, finding then the element of the matter that was kind of anticipated metaphorically by the Greek and 1,000 years ago. And then 100 years later, you have the Higgs that explain the reason why you have a mass into this element and where they exchange between each other. So it takes time. Science takes time. So we're just at the beginning. So we like the Rutherford experiment. So I have no doubt it's going to happen. And what I'm claiming is it would be an amazing moment because the difference can be striking between these different planets. Now, of course, when you reach this level, comes the questions, can we see the activity going on the surface of the planet? Can we say something about life? So right now, we don't understand very much this, but I want to give you some idea, some clue, how we are going to approach the problem. And that's when I say we, because it's not only a few people working together. It's a more global activity right now, teaming up different disciplines together. Okay. Oh, there is a text that didn't pop up here. It has been diluted by the system. So the text that should have been here, that is somewhere in the system, is a statement that Christian de Duve, Nobel Prize Physics, that produced in 2011 about this concept of life as part of a physical continuity. It's a bit what I said in the beginning, but practically it goes as follows, is the fact you have something alive on this planet, and the fact seems to be related to the chemistry of the planet, since the chemistry is related to the nature of the physics of how the component works together, and the existence of the components related to the nature of the law of physics you have in the universe, why life itself is not simply part of the law of the universe. So it's embedded. And if this is embedded, and this is happening here, it happens everywhere. Because the chemistry happening on that surface of that planet is happening on any planet in the universe. So the concept of life should be universal. So we should seriously think about that. Now, how could we find out what it means and whether there is a single solution or many solutions to end up? Well, it's a fascinating, complicated problem. And to just recall the difficulty of the problem, this is what I steal to my friends biologists about the history of life on Earth. It's a very nice diagram because usually we tend to forget when we see that the time. So it's a tree of life, but they added a time dimension, which is in log scale, that bring the timing of what it had happened. So if you look where we are, it's easy. We are here, human, just on the border here. There is the outskirt of this diagram. This is the today line. This is the famous 2D projections of the time. It's going, and that's what we have. We have all this amazing diversity of life that you can trace down to specific event that's going to trigger. Earth, for example, without the fact that the mass extension, the disappearance of the dinosaurs, and possibly related to comet or different event, that will not be talking here. So everything can be pointed to maybe a special event and there. So it's interesting to see the evolution of life as maybe a completely random process that depends on a lot of elements that happens, doesn't happen. That's why I don't really like very much the idea of radio ET looking, because it requires all this selection there. But the question of whether you start life as a kind of generic question is very, I think, is a foundation of the system, because at some point you have to start this. The challenge is the starting is there, early birth. And how do you connect this starting element with what you see? And that's almost an impossible problem to solve, practically, by looking at life as it is today. You have to come with different views. And this is why the new development of a planetology is interesting. Now, to make you understand why I think we are going to make a breakthrough into this field in the next 50 years, because that early birth moment is not now. So life cannot start from scratch on the planet right now. We don't see it. We don't see life happening from scratch. We see life being reproduced. It's a famous Pasteur study. I mean, if you put into vacuums and you sterilize something, no life will pop up naturally. There's not there life. Yeah, but if you don't sterilize, of course life will be, because they keep reproducing and being there. So it's a very interesting concept here, that life doesn't start right now from scratch. It just evolves right now. Why so? Well, because at the time life happened on Earth, it was not at all like today. It was a different scenario. This is the time that is making life. This is when life pops up. At that moment on Earth, the atmosphere is radically different. The structure of the surface of the planet is radically different. We believe there is only 1% of continental land at that time, very few. And an atmosphere very neutral, CO2 dominated, which is not the case right now. We have the ozone, the oxygen, all this right now in the atmosphere. So this is interesting bits. And why do I claim that there will be progress on that? Because until now, the only planet you could look at is the Earth. And unfortunately, there is very little left from that time on Earth, because everything has been reprocessed. The famous reprocessing, the plate tectonic, which is good because it maintains the CO2 within reason, doesn't end up like Venus. But we have process there going on, and by nature it destroys everything. Any continental crust, one day or later, will be sink and will be destroyed. There is still things you can get, because the buoyancy is still something that seems to since the early days, and there is still discovery to be made, I think, on Earth. Days, that element that never sunk and never got destroyed. They're always like a boat floating on the surface of the planet. You can see that way. So this is, I think, the interesting moment here. And we do have ways to study planet, because we have planet in that stage. We know them. I just mentioned 2 of them. There is plenty, and 2 of them that we know very well. They are a bit bigger, I agree, but they are warmer. I would agree, but that's fine, because at the early stage, the Earth was also warmer, way warmer. And early on, the planet Earth was even like a lava planet, because it was too hot, and it needs time to cool down. The fact it's hot is interesting, because there is all this interaction between the solid form of the component of the magma and when you get into the gaseous form. So this outgassing through the volcanic activity, this all brings back the CO2 and all the gas from the inside, leaving aside the human intervention, because we're doing also that for other reasons. We're bringing something inside and put it outside in the atmosphere. There has been always this on Earth. So the problem is, this is part of the complex problem. How do you evolve the Earth? How do you make the early Earth? But we can study planet in a similar situation, because they maintain in this status. They are too close to the stars. They kind of maintain due to the warmish of the energy coming from the star. And we have a quite substantial number of this planet, and we can study the atmosphere of this planet, as I told you. So we're going to add a lot of new elements to this massive puzzle which is the origin of life, by just looking at different planets that are not exactly like the Earth, but in a different situation, slightly different, or maybe adding this element there and there to patch up and get up the whole picture we have here. Now, another approach here as well is, can we make the origin of life? I mean, a kind of scenario. So there is three. A lot of the text is gone. I don't know why the white has been. This is a problem. I think the white has been removed by the system over there. I don't know who doesn't like the white. There is three ways that is understood right now to make life. I just want to share them with you because there are ongoing program on that. You may have heard. Unfortunately, this is the most commonly spread origin, which is the bottom of the oceans, black smokers, all that stuff there. And I think this is the most fragile origin of life scenario that we are to deal with. The problem is the dilution problem is a massive problem. I think the fact you form life into the oceans, I mean, life needs to concentrate, and you can't concentrate in the oceans. So I think this is almost of a killer no-no to form life with this way. Leaving aside, there is no chemistry, really little chemistry on that process. And the other big reason is if you go there, you don't see life happening so as well. So it's not making life as of today. So it's unlikely to be a source of life, but it's kind of mentioned many times. Another very famous way is the Urey Miller experience. They use a very energetic atmosphere, ammonia and methanes, and they have the discharge, and they produce all this energetic component. They manage to produce amino acids and foundations of even some nucleotides in the experiment, and I think it's very interesting. The challenge here is the atmosphere that they need to make the experimental work. No, in chemistry, you know chemistry a little bit. It's about moving electrons. So to move the electrons, there is three ways to do that. One of them is you shake, because some of them are willing to move. It's what makes the explosive. The other one is you bring heat. So it's when you cook, you make food. This is the chemistry you're doing, because you bring the temperature up, and it allows to break some of the bounds and to help changing the bounds around. The third one is you irradiate with a UV lamp. Very powerful, is commonly done in chemistry to stimulate the electrons. So you need this kind of element there. So the problem is, of course, if you have a lot of energy into the atmosphere, which is the case of the atmosphere they're using, it's extremely unstable. So as soon as you have energy in the atmosphere, you start making new component. And I think the fact you sustain the atmosphere long enough to make life is unlikely. You need something happening. In that case, it's bombardment from comet. So the only way to produce this kind of very special atmosphere is to have a lot of ammonia, a lot of methanes, and then having this bombardment from comet. It's possibly what has happened early on, but you need to replenish the bombardment in a way you always bring back this instability. You have to build up a pseudo-stable situations where you fight against the natural chemistry that tends to go neutral, and then the energy you bring in. Interesting element to mention, Titan, the satellite Titan on Saturn, is believed to have an atmosphere of that kind. That's why people are very excited to go on Titan, to study the atmosphere of Titan, because this is what you may encounter there, this kind of scenario there. Currently, the most commonly understood scenario is what is being described by cyanosulfidic chemistry, or HCN chemistry. It happens on the surface of the planet. It's related to the UV radiations from the sun. At that time, there is no ozone, so there is plenty of UV beaming on the planet, helping producing the chemistry. This is the biggest in my diagram because this is the most advanced scenario. There is a series of publications right now on that since about 2015, and people are trying to use this scenario to make life in the lab. They're very advanced. I mean, amino acids, nucleotides, lipids producing the cell is being produced, all this together, and one day you may heard that somebody in the lab has produced chemistry of life, at least to produce something which is a proto-cell, in a sense, into a lab, and that will come from this chemistry, I'm pretty sure. And that is something that is developing and growing right now. It's interesting for me, not as a chemist, but as an astrophysicist, because there is a series of predictions being made about the nature of the atmosphere, the element that is needed, and the condition you need on the surface of the planet to be met for this chemistry to happen. You can think about any chemistry, if it's not related to reality, it's science fiction. So it means it leads nowhere. It's like if you start a theory, say, no, let's go faster than the speed of light. Okay, it's unlikely it has any reality at all. It's fun maybe to do it, but it doesn't lead nowhere. So I think this is a good stuff here. We have to add boundary conditions into the chemistry of life, into the reality. And the fact we have now more and more data on planet bring this reality check that we're considering. Another big step into this, this field is what is going on Mars. Why Mars is so exciting? We know that Mars, within the first billion years, had water on the surface. It's possible the chemistry of Mars is similar for the first billion years, the chemistry of life on Mars. And if it's the case, then you should expect some leftover. Don't expect to see an animal and something crawling there, and that's not what we're talking about. We're talking about something that is connected to the early chemistry of life. Chemistry of life is very different from chemistry in organic. You do that. It produces a different set of different ratio of chemistry. You may have different isotopes as well. You well know the carbon-14 is isotope trick to date things. So you can really replicate that at a high level to many different elements here. Of course, to study that at the level we need, which is really a lot of digit behind the zero here, this very, very tiny difference that you're looking for something left over, you have to bring it back. The robot is cool and the helicopter is fascinating, but they don't do very much. And they are very limited because they are limited equipment. So they can do basic geophysics, which is extremely useful. We know there is water, they can pick the rocks, they can do a lot of interesting, but what is going to happen, which is really a big change, is when you are going to bring back the stuff from Mars. It's collection of the sample are being collected right now. They will be brought back by a mission in 10 years, and then the fun will start, because then we will have component on Earth. We can study that in great detail with all the equipment we have. When you think about that, last time it happened, it was 50 years ago, when we brought back a sample from the moon. The moon is interesting because it tells you something about the history of the Earth. You know, the moon was formed about 20 million years after the formation of the Earth as a result of a major impact. So the composition of the moon is exactly the same than the Earth, essentially, of the mantle of the Earth. So it timed the event and gives you an interesting boundary condition for the history of the Earth. But it's nothing like Mars. So this is really why people are very, very excited. And hopefully, mission to Venus one day will do the same, because Venus may well have had a similar situation in the first billion years. We know that there is no water right now on Venus. That is the reason why it's fully a greenhouse final on Venus. But with water, you would never end up like that. So how come do you lose the water? Was it because you had not enough water from the very beginning? Whether because there's too much irradiations from the sun at a specific moment when it was not really, the response was not from the planet was not ready to respond to that. We don't really know. So Venus has been unknown here, and we would love to know very much. Okay, so I will just finish on this by this kind of generic statements. I hope you understood something here. Physics is a foundation in terms of science. It leads to many things, and you end up with having physicists in every discipline later on. So you may start physics, you end up with something else. I started physics because I didn't know what to choose, actually. And I'm very glad right now. I thought physics, whatever I do, I will learn something, and we'll see later. No, I'm quite excited right now at the end of my career to work on that topic, origin of life, because I happen to relearn chemistry and to work with colleagues and sciences, and to realize we're all doing the same things. The only tiny difference or culture or jargon element, but essentially the way, the rational approach, and this kind of curiosity-driven element is the big motivation. So I really welcome you into the world of science, whatever you will be doing, and hopefully maybe some of you will be working on that topic. You understood there is room for many, many different kind of work on that topic. Thank you very much.
Thank you, Professor, for your inspiring talk. Thank you. We have room for some questions.
Sure.
So please, I see some hands.
Hi, thanks for the talks. I wanted to go back to a specific topic of dilution because I think about disorder system and it seems like we can have localization in such system. So you were like saying that we need element to go together, but if we have some localization, well, I think we may have life. And so I just wanted to you to explain a little bit more what you were meaning with dilution.
Okay. Well, there is plenty of problem with this black smokers and dead city origin of life. It's one of the many which is easy to pitch, which is the idea of concentrations. Let me give you an example. Let's imagine you want to make the chemistry of life, and you have two options at some point, because chemistry is competing. You understand that the chemistry is going to happen. Whatever you do, you all cook, it will end up with something. Whether it will be something you can eat or not depends on how you deal with the chemistry here when you're cooking with the same ingredients. So my point here is, whatever you do, you need to concentrate the pathway to life into a completely successful process. Now, at every corner, you end up with a different chemistry. It's a chemistry problem. So think about a lot of turnover when you end up with shampoos or something different and soap, and you don't produce life. You produce fantastic chemistry, but not life. The problem of life is to always to fight against this and to end up with the best way. The only way to be successful into that is to be the fastest, the more efficient process, and to collect all the elements better than any other process. So to do that, you need a lot of element of chemistry, of course, yield, but you need to make sure you have the element around. So the more you build, the more you need. So you need the concentration is embedded to get it. That's why people are looking for phosphorus lake or this kind of element there, because you need this concentration element, which is the biggest challenge of the chemistry. How do you get up enough element to develop the chemistry of life in a way you always have enough? Otherwise, you create something and you die after that. So this is why it was mentioned as a big issue here. The other big issue is there is no chemistry essentially on this, why the other mechanism has a chemistry so it can be tested. But again, since nobody has been successfully today produce something alive in a lab, the game is open. And maybe these people will just find out somewhere to process it. But I agree it's nice to get a thermal vent and there's nice chemistry going on. Maybe it's a mixture of everything. Maybe you need the comet falling, you need also the thermal vent, you need also the UV. It's just the beginning. It's just I don't have an answer here.
Yeah, thank you. Thank you.
Thank you a lot for a great speech. I would like to ask about the magnetic field of the exoplanet, if there is any possibility to detect it, or even some ideas what we should watch to detect it, like what effects and things like that.
Wow, okay. Well, yes and no. It depends on the planet. And if you think about the magnetic field in a generic way, yes, there are. In similar way that we have detected the magnetic field of Io. So the magnetic field of Io, the interaction with Io and Jupiter was detected with radio astronomy. So radio astronomy can detect cyclotronic emissions. You need very big telescopes. So SKA may be doing that, or maybe the future moon-based radio machinery will do. Of course, you need a very energized interactions to do that. If you try to detect the collision between the electrons hitting the magnetic field of the Earth, that is really marginal. So I don't think there is any prospect to do that practically. So that is a difficult parametric value. I know it's critical. It's seen as critical for life, possibly. It will take a while until with that, but who knows? I mean, you know, one day there may be a massive moon base on the dark side of the moon, and with a gigantic radio telescope, and they may be pointing to a system that is well understood, well studied, with a specific purpose to look for that interactions. But it's challenging.
What do you think? What are the possible future methods to detect those different types of atmospheres that you would see in systems with life? For example, I remember some proposal to detect some specific infrared wavelengths of molecules that you'd find only in living systems on Earth, at least as we know now. So what do you expect that could happen maybe next 10 years in this field?
Well, I think we can detect anything on the upper deck of an atmosphere, given you have enough signal. So it depends on the ratio between the planet size and the size of the atmosphere and the star. The biggest the molecule feature will be, the easier it is. So what is the easy molecule to pick? Water, CO2, they're very easy to detect. There is massive absorption of CO2 on water. I think these are pretty easy, and it's being done right now. Now, detecting this molecule on smaller planets is more challenging, but it's certainly possible. And then you can push back and you can continue and look at some other specific molecule. It's how much signal you will get at the end. Technically, you can get anything which is in the upper deck. What you can't get is what is below the deck. And the reason why I mentioned that, if you imagine some other civilization looking at the solar system and studying Venus, for example, they will find Venus habitable because they would only see the upper layer of Venus. They will not see, and it has happened. I mean, until the 60s, 70s, there has been paper on Venus that the Venusian civilizations that nobody really thought that it would be so hot. It came later on when they started to study the atmospheric structure of the planet. But looking only at the outskirts, you see just a layer of cloud, nice temperature, you pick up some interesting molecule, you say, well, there is not really water, that's a problem which is missing here, but you have other interesting molecules. So I think what is going to happen in the future is we are going to deviate from the limitation of the transiting techniques, because transit is very limited. It has to be short period planets. It's a very brief moment. So essentially, nothing is happening until the planet goes in front or behind, except that if you can do the phase curve experiment, which is limited to few systems, very bright, you really need to see the planet. And I think this idea of a new generation of telescopes, likely in space, but are going to see the planet. So you remove the star, you use tricks to do that, you remove the star, and then you study the planet. And if you really be able to make a picture, like the famous blue dot picture, remember, of the Carl Sagan stuff, then you can see maybe a change on the atmosphere. You can maybe see the diurnal rotation. So you can see maybe seasonal variation. You can see a lot of effect because you can keep tracking the planet around. It's not for now. You may be seeing it because when you see the progress in science in 50 years, so you go back in the 80s, I think it's tremendous what can be done, especially the space industry. So I expect a complete revolution in space industries. It's already going on, but in the next 20 years. So who knows? But technically, you don't break the law of physics here. You don't need to go faster than the speed of light. You don't do that. The problem is if you want to go to the planet. That is more complicated because then it's really challenging in terms of time and data transfer, energy, and then you cannot break the law of physics. So there is a very challenging situation here to just go there and to send a probe to another planet. But as far as you remote observe, it's okay. You can do really a lot. You can do a lot, but you don't touch.
Thank you.
We have room for one last question. So,
thank you for the talk first. Just one question. Were there already some examples where more than one planet was discovered for a star? Or is this even possible?
Oh, yeah. I didn't mention this, but most of this, well, thank you for this question. So most of the small planets, they are not alone. They really are into a system. Sometimes the fact they are into system helps to find out the nature of the system, like the TRAPPIST system. I mean, this resonance, 6 planets talking to each other, you get the mass out of that. So there are, yes, the formation of planet is not only one. So usually it's many at the same time. When you detect them, you are biased. You pick up the easy one first, and the second one, and the third one, and the fourth one, and then the more you observe, the more they are. So it may well be that a lot of the system for which we know only the short period ones, when keep observing them, we are going to find out there is a bit more remote one, and one day we'll find that there are a couple of 5, 6 planets like Venus until you are detecting a planet like the Earth a bit further out. It's possible. So this is about to come. So yes, they come into a series. That's absolutely correct.
Thank you.
I'm turning my head to the organizer.
Yeah, sorry. Here we are. So again, thank you, Professor, for coming. Thank you for your inspirational talk. We have, again, a gift for you because, you know, it is a real pleasure for us.
Thank you. Thank you. Thank you.
I'll take this.
And the famous Italian champagne.
Yeah.
Good. Very good. Thank you. Thank you very much.
Pictures. Thank you. Thank you. So, sorry, this is yours.
Yep.
Okay. We are going to have now the coffee break. So please, slowly, you will find 5 coffee machines. You will find also some little things to eat there. So we have almost 15 minutes, and then we will have the poster session. Okay? Thank you.